So this is G481 homework booklet question 18. Nice little question about materials. Starts off with a stress strain graph, and it asks us to sketch a stress strain graph for a typical ductile material. It's important that you don't get carried away with the word sketch. Sketching does not mean do it roughly, does not mean gently. It just means we haven't got all the numbers. Very often you'll even be sketching a graph where you have got some bits of data. So they might have given you, for example, they could have given you the yield stress, which would have been that value there on the stress scale. If they had, you ought to be putting that on the axis. So you're always trying to get as much detail as you can into these sketch graphs, and that perhaps shows itself with this question. Ductile material, you should always be starting with the straight line and then it should be curving over. There's only one sure way of showing the examiner that you understand that initial section should be a straight line that should be passing through the origin. That's by using a ruler, so please, well worth making sure you do. Again, we've got the next one, circle of list below a material that is ductile. The classic materials which are ductile are metals, so very straightforwardly, hopefully out of there should be jumping copper. It's interesting, these first two, we've got sketch, which is something you do to a diagram, and circle, something you do there. Neither of those give some nice little dotted lines for you to answer on, and there's always a danger of missing those out, so it really is important that you read those very, very carefully. Next, we've got to define the ultimate tensile strength of a material. It's the maximum, and it's a stress, the maximum stress that a material can withstand. So that's what the key for that. And it's state Hooke's law, so the extension is proportional to the force as long as the elastic limit is not exceeded. Again, whether it's defined or it's stating a law, they're on your definition cards. If you want to try those out of your head to start with, that's great, but by the time you hand this in as homework, do make sure you've checked those against the card. That's the point. Opportunity for you to check and make sure of your learning there. Part E then is actually half the question. It's a great little question about a table tennis ball launcher. So it says that the diagram shows a mechanism for firing a table tennis ball vertically into the air. So we've got a platform with a spring, and we just pull down on there, compress the spring and release, and off it goes. So we're given information about the force constant, 75 newtons per metre, and it's compressed by that much, and we've got to calculate the force exerted by the compressed spring on the ball immediately after it's released. Assume both the spring and the platform have negligible mass. So first up, we're just after working out the force. I've got a force constant, I've got an extension, F equals kx, force constant times the extension, I'm getting 3.68. I'm giving the answer as 6.4 newtons. We're then given the mass of the ball. We've got to calculate the initial acceleration. Well, the initial acceleration is when we have got that extension we were looking at, so we have got that force. So I've got a mass, I've just calculated a force. That's straight away making me think about F equals ma. Put in the data I've got, rearrange it, 6.38 over the 2.5 times 10 to the minus 3, and I get an acceleration of 2,550 meters per second squared. Part 3 is the tricky part of the whole question. However, reading the question really carefully again is absolutely crucial to doing an effective job with this. It says calculate the maximum height that could be gained by the ball. Assume all the elastic potential energy of the spring is converted into gravitational potential energy of the ball. That's the clue. Assume all of the elastic potential energy of the spring is converted into gravitational potential energy of the ball. So straight away I think, so what I'm going to do, I'm going to convert the potential energy I had stored in the spring, half fx squared. I could have used a half kx squared. I chose to use a half fx. And then that is equal to mgh, the gravitational potential energy is going to end up with, because we're assuming, as it said in the question, all of the elastic potential energy of the spring is converted into gravitational potential energy of the ball. So I'm equating those two things together. mgh is a half fx. So there's the mass, there's g, there's h, a half times f times x. In that context, rearrange that, and it turns out that the ball can get 11 meters up in the air. There's no way it would, because in practice that's going to experience substantial air resistance, and the air resistance will do work and convert some of that energy into thermal energy, but on the assumption that you were told to take 11 meters. So that's G481 homework booklet question 18.